So let's just change the problem a little bit, right? Because we have billions of reads and we have to combine them all together. Can we also look at the problem in a different way, which is instead of creating a data structure that holds all the patterns together, can we create a data structure from the genome itself? How do we pre-process the genome, right? We are looking at the reverse problem. Instead of building a data structure to hold all the patterns, let's build a data structure that try to hold the different substrings of the genome, specifically all the suffixes of the genome. Okay, we will split the genome into all its suffixes, and then we will show that banana can be matched by finding the suffix bananas. Okay, show matching banana by finding the suffix bananas. If there is no suffix that starts with banana, then you know that the pattern banana will not match the genome. Okay, that is the idea. And how can we combine these suffixes into a data structure? Again, we can use a trie. Okay, let's just see this, how it works. This is our genome. We are going to look at all the suffixes of the genome and we are going to build a trie for that. Okay, the first suffix is the full string Panama bananas. Right. The next suffix is going to be Anama bananas. Right. The next is going to be Nama bananas. Then it's going to be Ama bananas. But for those next suffix Ama bananas, it's not going to be a separate branch. The A is going to be shared, right? So you have A which is shared here. This is Ama bananas, and a dollar is like a special symbol that you add just so that all the leaves have this special symbol. Okay, the usual English letter A to Z is augmented with this additional letter dollar, which is a special symbol that will terminate these strings. Okay, we will see why this is useful later on, but it's a good kind of ending character or sentinel character to have, a special symbol. So you have Ama bananas dollar, so that will share A for Anama bananas, and then you have Ma bananas, right? So that is how it is. Then you have another then you have the next suffix is Ma bananas. Then you have A bananas, right? So the A is again shared here. Then you have bananas, right? Then you have ananas. Here you can see here that when you go from bananas to ananas, A and A are shared with an earlier suffix. Okay, this A and A here and this A and A here are being shared. So substrings of this genome which are shared, right, will lead to sharing of these edges A and A, right? Then you have Ma bananas going down this, and then ananas going down this. Okay. Then you have nanas, right? Again, you can see here that Na is being shared. Ananas, Anas dollar, Nas dollar, As dollar, and dollar. Okay, S dollar, and finally you will have a dollar. The dollar you are ignoring, so the final one is S dollar. Okay, dollar is not really a suffix; it's just the special symbol, so you don't add anything for a dollar. This is your data structure that compactly represents all the suffixes of your genome. Okay. Now if you want to find a pattern, you just have to scan the pattern in this particular data structure. Okay, the advantage of building this data structure is that the reference genome is always going to be the same, right? So you can pre-process your reference genome and build this kind of index. I will call this the index of the genome, right? So this is a data structure that will make searching patterns in the genome very efficient, right? And now the reference genome is always going to be the same for the humans, let's say. Now if different personal genomes come, right, different patient samples come in, then they can be different reads, and all those reads can be scanned into this same data structure for the reference genome. Okay, you don't have to construct a trie for each of the patient's samples, okay, patient's reads. So like I said, for each pattern we want to see if the pattern can be spelled out from the root downward in the suffix trie. So if you have a pattern called banana, then I am looking for whether banana can be found in this suffix trie for this genome. Okay, so it indeed can be, but it did not go all the way till the leaf. Okay, because your pattern need not be the full suffix, it can be a prefix of that suffix. Okay, so banana is a prefix of bananas. Okay, and it is still considered a valid hit in this particular trie. Okay, similarly nab, so you go down Na, but there is no such B after Na, so this NAB is a pattern that is not found in the genome. Okay, then you are looking for antenna. Antenna T is also not found after A and N, so this is also not a hit. Nana is going to be a hit. Right, so this is how a suffix trie for the genome. So this is going to be, this is your suffix trie of the genome that holds all the suffixes of the genome, and these are patterns that are now scanned one after the other into this across this trie, right? But Nana is present here, but how do we know where it is hitting, right? Where in the genome is this? So the genome, the full genome is Panama bananas, right? How will you know where Nana occurs? So we know that Nana occurs here. We can just scan visually, and then we can say that Nana occurs over here. But how do you store the positions in this data structure so that we can return that Nana occurs in this location 1, 2, 3, 4, 5, 6, 7, 8, 9th location, right? I want you to think about it a bit and then see what attributes can you add to some of the nodes in this trie so that you can remember the location where it is coming from. So this Nana's dollar, right, is occurring at location 9, that is the 9th suffix. Maybe I can add 9 over here in the final node, right? And the Panama bananas dollar is the full suffix, right, the full string, and that is starting at location 1. Maybe I can say here that this is location 1, right? So the final node will have an additional attribute that will store the location of where these suffixes are beginning, right? To find where the locations, the patterns are matching, we'll add this information. At every leaf we add the starting position in genome of the suffix ending at that leaf. Okay, like Panama bananas is going to be actually they are okay, so we are computer scientists, so we will use numbering that starts with 0 rather than 1. So Panama bananas will be 0th location. Anama bananas would be this one, right? A, this one, ANAMA bananas. This is first position. You have the second position is Nama bananas and so on. Okay. NA's dollar is 10th, AS dollar is 11th, and S dollar is 12th. Okay. So where are these matches, right? So once we find a match, we walk down to the leaf in order to find the starting position of the match. Okay, so that is the algorithm for finding the locations where the matches are. So for instance, if you have banana, then you go down this and then you will see that banana occurs at location number 6, right, which is indeed true because banana is at 0, 1, 2, 3, 4, 5, 6, right? That is where it is indeed occurring because banana is a prefix of the suffix bananas dollar. All right. This is a bit more interesting example, ANA, because this ANA is going to occur at multiple positions in the genome, and this data structure will capture all those positions because ANA will stop here, and then now at this root there is a subtree here, and this subtree has 3 different leaves. So you can do a depth first tree, a search here, for instance, a traversal, and then you can go down this branch and you will see that this is dollar. You can This is 1 at location 1 it is matching, and then you can go down this to see at location 7 it is matching, and then go down here to see at location 9 also it is matching. So A and A is going to match it 3 different locations, 1, 7 and 9, and which is indeed pointed out here, the location 1, location 7 and location 9, which is indeed true. You have these 3 matches, A and A at location 1, A and A at location 7 and A and A at location 9. Okay, and some of these hits may overlap, like the 7th and the 9th location. Okay, again remember that these are the locations or positions. We are starting with a 0-based numbering. Okay, so the problem with memory once again, so this may look like we have solved this problem of we don't have to construct this trie every time the patient changes, whoever is coming to the clinic, or every individual changes. We only have to construct this trie once for the full reference genome, and then the reads from a patient can be then scanned through this single trie data structure, right? So that is good, but then there seems to be also too many letters around, right? You can see here that the genome is just copied multiple times here, right? Because all the suffixes are being considered. If we don't do anything clever on top of this, this is going to take size quadratic in the size of the genome, because you're considering all the suffixes. So the first suffix is n in length, if n is the total size of the genome. The next is going to be n minus 1 in length, n minus 2 in length, n minus 3 in length. So if you add it all up, you will get order of n squared, right? So it will be quadratic in the size of the genome, and that is what is shown here. You are storing all of these suffixes, and this is n plus n minus 1 plus n minus 2 plus n minus 3 plus all the way to 1, and that is going to be n into n minus 1 over 2, which is order of n squared. Okay, so so in the worst case, the suffix trie which holds order of suffixes nodes, even though it makes it easier to scan patterns against a single suffix trie constructed from the genome, this size is really prohibitive. Okay, can we do something to make it linear in size? Or specifically, can we compress our trie? Okay, so to do that, we are going to look at every non-branching path and convert it into a single edge. So we are not going to have one edge per letter. We are going to have edges only to represent branching points. So let's look at this. There are many non-branching paths in this particular tree, right? So for instance here, all of this is a path through a series of nodes and edges, and none of these nodes have anything other than an incoming and an outgoing edge, right? All of them are degree 2, right? They don't have branches like in this particular node you have one incoming and then 3 outgoing edges, right? But all of these have one incoming and one outgoing edge. So this is a branch, a single branch, but then all of these are not branching. These nodes are not branching further into any other branches. So all of that you can just represent it as bananas dollar. Okay. Similarly, this non-branching path, you can call it as ma bananas dollar, and so on. Okay. This is going to be ma bananas dollar, nas dollar, s dollar, and this will be na. This will be again s dollar, ananas dollar. So all of these paths which do not have any branches, right? So these non-branching paths can be compressed into these strings. Ma bananas, na s dollar and na. Panama bananas, the full string, s dollar. Okay. So this looks much smaller, right? There is not these too many nodes there, but still these strings are all very long, right? So I mean, you still need to use so many number of letters. So Panama banana, all the suffixes are still being stored, right? Panama bananas is being stored. In the worst case, if there is no sharing, then Anama bananas will be stored, right? Anama bananas is stored. Nama bananas is stored. Nama bananas is stored and so on, and it still looks like we have not done any compressing really. But think about it, right? So is there any way in which, regardless of the length of this sequence, can we store this sequence in a very short compressed way? Okay, I'm going to let you think about it for a bit. Do we have to really store all these letters, right? All of these are suffixes. All of these are contiguous locations in the genome. Okay, does that give you any idea on how you could compress the space used for storing this? I'm going to elaborate that a little bit more. This is your full genome, reference genome, Panama bananas $. This you store it once, so that is going to be order of size of genome. But then if you look at all of these things, these are going to be substrings of this genome, right? Panama bananas is going to be the full string, so I can just say it starts at location 0, ends at location 13. Similarly, Ma bananas $, is going to be a particular location in the genome, right? So this is going to start at this position and end at this 13 position. So this position is going to be 0, 1, 2, 3, 4. So this can be stored, Ma bananas can be stored using 4, 13. This Panama bananas can be stored using 0, 13. Just two numbers, right? Whatever the length of the string, we know that they are all contiguous. They are next to each other. All these letters are next to each other in the full genome. So if you store the full genome only once, then all of these substrings can be stored using the starting and the ending position of these substrings. Okay, 4, 13 for Ma bananas, 0, 13 for Panama bananas, and so on. Okay, this will also be 4, 13. Na is going to be this one. Na is going to be just 0, 1, 2, 3, right? So Na is going to be 2, 3, and so on. What we previously had was a suffix trie, but this now, where all the non-branching parts has been compressed, and each of these substrings are now represented with two numbers, which is the beginning and ending position of that substring in the full reference genome. That data structure is called a suffix tree. So for any genome, right, the number of nodes here is going to be less than 2 times into the size of the genome. Why is that? So the number of nodes in the tree is the number of leaves plus number of internal nodes. The number of leaves is the size of genome. The number of internal nodes is also at most the size of the genome, because we have removed all the non-branching parts. Okay, so it has been compressed and compacted, and so we have a linear in the size of the genome. Like we said, the number of leaves is the size of the genome. The number of internal nodes, in fact, you can say if each of the internal node, excuse me, there is one typo here, this has to be green as well. This should be green as well, but all the internal nodes are only 1, 2, 3, right, excluding root. So that has to be at most, strictly at most, genome minus 1, by just following the property of a tree where each internal node have at least degree 3. Number of partners is 3. So even though the final running time is linear here and linear here, our steps to get there, we had to spend some quadratic time, at least in the algorithm that we have seen so far. Okay, you can have algorithms that will construct the suffix tree directly in linear running time and in linear space, okay, using linear memory directly without having to go through this suffix trie and then compress it into suffix tree. Okay, so this is possible. So then this gets rid of the quadratic limitation, right, the quadratic running time and space, and gives you linear space and running time to construct a suffix tree and to find all the pattern matches. Okay, so that is good news for us. And so the total runtime is linear in the size of the genome and patterns, and the total memory is also linear in the size of the genome and patterns. Okay, so this gives us a data structure called the suffix tree. Though we haven't looked at how this direct algorithm works, but let's take that by faith, right? So that there are algorithms that exist. There has been a lot of work done on that, and different types of different ways in which this direct construction could happen, right? And it's nicely summarized in Dan Gusfield's book on algorithms on tree strings. Um, so we can refer to that book for some of these algorithms. It is also mentioned in the original works. So Gusfield, algorithms on strings, trees, and sequences. Okay, so that goes into a much more detail on how to construct these suffix trees directly. Okay, but for the purposes of this course, we won't get into that. We will look at what are the advantages of having this suffix tree data structure. Okay, now that we have understood that suffix tree is a compressed way of representing all the suffixes in a particular genome, and this allows us to match patterns in linear time. Okay, so let's look at how we can take this further. Okay, so what we have seen so far is suffix trees, which are very compact ways of representing all the suffixes of the genome, so that you can do pattern matching in efficient, both time efficient and a space efficient way. And efficiency, to the extent, maximum extent possible, is basically linear, right? So the size of genome plus size of patterns is, with some constants hidden there, is what the suffix tree will allow, both the construction of the suffix tree as well as pattern matching, okay, like we have seen here.